Module 1, Topic D, Isosceles and equilateral triangles. This is going to go with Lesson 23. And quite a bit of review here to start with. Remember, we defined isosceles triangle as a triangle with at least two congruent sides. We said that equilateral triangles are just very special isosceles triangles. There's our two congruent sides. That means that this will be our vertex angle and that these will then be named our base angles on the base of our triangle. You have your legs, your base, your vertex angle, and your base angles. A review of our theorems. The isosceles triangle theorem says that if two sides of your triangle are congruent, then the angles opposite those sides are congruent. So that one's an easy one. We know it. The converse says if your two angles are congruent, then the sides opposite those angles are congruent. So we can mark our sides congruent. And our awesome theorem said that if a line bisects the vertex angle of an isosceles triangle, then it is also the perpendicular bisector of the base. So this is really just an awesome theorem. If we have an isosceles triangle and we have an angle bisector, then we can automatically say perpendicular and bisect. Remember, those are two different things. Perpendicular means we've got right angles, and bisector means we've got two congruent parts. We have a nice little proof of the isosceles triangle theorem here, and we are going to use side angle side to prove that. So if we are given an isosceles triangle, that means we know that those sides are congruent. We want to prove that those two angles are congruent. Remember, all theorems are proven. So the first thing we are going to do is we are going to construct the angle bisector of our vertex angle. Easy enough. We know how to construct with our compass an angle bisector. And so we now have these two congruent sides, a congruent angle, and just can't help myself here. The reflexive property of congruence says that that segment is congruent to itself. And now do you see side angle side? We are given our two legs. Reflexive property gives us our sides. We constructed an angle bisector, so by definition of angle bisector, those angles are congruent. That means that our triangles are congruent. And once our triangles are congruent, what can we do? We can say that any other corresponding parts of our two triangles will be congruent. CPCTC. So that's a nifty little proof, isn't it? Isn't geometry fun? Some examples of using isosceles triangles. What I want to know is segment AB, that's this one, congruent to segment CB. Why, yes, I believe it is. How do I know that? Because I have two congruent angles, which by the converse of my isosceles triangle theorem says that my two sides of my big triangle here must be congruent. So that one was easy enough. And then part B is angle A congruent to angle DEA. Where's angle DEA? We're looking at angle A, and we want it to be congruent to angle DEA. Why, yes. Yes, it is. That's just the isosceles triangle theorem. My two legs are congruent, therefore my two angles are congruent. All right, given this triangle, we've got an isosceles triangle. Automatically see that. That makes me want to mark my base angles congruent, isosceles triangle theorem. So as soon as I mark those congruent, I feel that I must label angle C 54 degrees. And what else do we know? I haven't even looked to see what I know yet. We've got a big triangle here, ABC. Look at triangle ABC. We can find the measure of this top angle, this whole top angle here, by the triangle angle sum theorem. And then we could just cut it in half. Or we know that this angle up here is being bisected, which means that that is a right angle, which means we could use triangle angle sum theorem. We know these are 90 degrees, and then find angle x. So we have a number of ways of doing this. We could say that 54 plus 54 plus the measure of angle ABC equals 180 degrees. And so that's 108 minus 108 on both sides. The measure of angle ABC, 72. And then if I divide that in half because it is bisected, we get x equals 36 degrees. Hey! So it doesn't matter. This is just triangle angle sum theorem. Doesn't matter which way we do this. Thank you, geometry, for giving us multiple ways to answer each question. So we can use our awesome theorem, or we can just use our isosceles triangle theorem and triangle angle sum theorem. And finding angle measures. Let's see. We want to know what are the measures of angle A, B, and ADC. So we are looking at angle A, angle B, and angle ADC. So this big one right here. Well, I see equilateral triangles, and we know that equilateral triangles have angles that are 60 degrees. So this one is 60 degrees, this one is 60 degrees, this top one here is 60 degrees, this one over here is 60 degrees. So the measure of angle A is 60 degrees, angle B is 60 degrees, and the measure of angle ADC is going to be 120 degrees because we simply add them together. And an example proof for us. Angle B and angle C are congruent. Angle K and angle A are congruent. And we are told that angle KBC is congruent to angle ABC. So this one and this one are congruent. That means that they're also congruent to C, that we could use transitive property. So maybe a transitive property here. What am I trying to prove? That KB is congruent to KC. I want this to be an isosceles triangle. I want those two to be congruent. I've got two angles that are congruent. That means that I can say those angles are congruent by my third angles theorem. And because these two angles down here in this corner are already congruent, I'm going to have an isosceles triangle by the converse of the isosceles triangle theorem. So let's look and see what we did. There's our three given angles. We make those angles congruent by the third angles theorem. I'm thinking there probably should have been a transitive property here in the middle somewhere. Transitive property of congruence, making those angles congruent. Angle KBC would be congruent to angle KCB, which would let us use the converse of the isosceles triangle theorem. I need to edit more carefully, apparently. But you can see how defining and exploring and labeling your diagrams is going to make all of the difference. Let's go enjoy doing some more side angle side proofs, now with the added fun of isosceles triangles.